In this video, we'll discuss elementary rate laws. And the important things to remember about when dealing with rate laws are to get both your units and your signs correct, because those are easy to mistake here. And our rate laws can be related to each other in the same reaction, relative rates, through the use of the stoichiometric coefficients in our reactions. This can be demonstrated if we take an equation like 2a goes to b. And let's say that we know that the rate of formation of B, R sub B, is equal to 4 moles per cubic meter per second. Then our rate of disappearance of A minus RA over our stoichiometric coefficient, which in this case is 2, is equal to our rate of formation of B, a product, which is 4, over its stoichiometric coefficient, which is 1. So we can see that minus RA, our rate of disappearance of A, is equal to 8 moles per cubic meter per second. Or alternately, that RA, the rate of formation of A, is equal to minus 8 moles per cubic meter per second. It's important to keep these straight and to realize that the rate of formation and the rate of disappearance are really just negatives of each other. Now, especially with elementary rate laws, we'll be working exclusively with the power law model. Rate law data is determined experimentally, but it can be modeled dependent on the concentration of the reactant species. The powers to which these species are raised is dependent on the stoichiometric coefficient in our chemical reaction formula. So for this model here, minus Ra is equal to Ka times Ca to the alpha times Cb to the beta. We say that our reaction is to the alpha order in A and to the beta order in B, and our overall reactant order, N, is equal to alpha plus beta. Ka is our specific reaction rate constant, and the units here are going to be something we want to keep track of, because depending on the overall order of the reaction, the units are going to change. We can see this because minus Ra is always going to be in units of concentration per time, and so the units of our specific reaction rate, K, are always going to be concentration to the 1 minus N, the reaction order, over time. So an elementary irreversible rate law for an equation like 2a goes to b would just simply be minus Ra is equal to Ka times Ca squared. And for irreversible reactions, we're only going to be looking at the reactants. Now, for reversible reactions, our elementary rate laws get a little more complicated. Take, for example, our reaction 2a reversibly goes to b. We can look at this as really two reactions where 2a goes to b and b goes to 2a. We still want to write our overall reaction rate with respect to a here, and so Ra is going to just be the sum of Ra forward and Ra in reverse. Going forward, this is the same as we did before, so we'll have Ra, let's put F for forward, is equal to Ka Ca squared. Ra reverse will be K, we'll use our subscript minus A times Cb, since that's our reactant. The last thing we have to introduce is our equilibrium coefficient, which will be capital K sub C. This will be defined as our forward rate constant divided by our reverse rate constant. Adding our forward and reverse rates together, we can factor K sub A out, and we get that Ra is equal to our forward rate constant times Ca squared minus Cb over our equilibrium coefficient. The important thing to remember for elementary rate laws is that the exponent will always match the coefficient in the equation. Of course, there are many other types of rate laws, and we'll learn about some of those later, but this will work for now.